July 17th, 1996. John F. Kennedy International Airport, New York. A sweltering summer evening. TWA Flight 800, a routine service bound for Paris and Rome, was an aircraft of high hopes. On board were 230 souls, families, business travelers, and a group of high school students on an eagerly anticipated French club trip. The cockpit was manned by a seasoned crew: Captain Ralph Boy Kevorkian, First Officer Stephen Snyder, and Flight Engineer Richard Campbell. This was not a flight destined for drama. It was a simple journey. But before they ever left the ground, a fatal process was set in motion. A long delay at the gate forced the crew to keep the powerful air conditioning packs ACMs running for hours in the extreme heat. The ACMS, located directly beneath the center wing fuel tank, CWFT, acted like a heating element. In the near empty tank, containing only about 50 gallons of residual jet fuel, the heat baked the fuel, turning the inert fuel air mixture into a highly volatile, highly combustible gas cloud. An engineering vulnerability, overlooked for decades, had quietly armed itself. At 8:19 b.m., the jet lumbered down the runway and lifted off. 12 minutes later, as the plane leveled out at 13,700 feet, the final, unseen variable came into play. Down in the belly of the 25-year-old aircraft, the fuel quantity indication system, FQIS wiring, which runs through the CWFT, had been subjected to years of electrical stress and potential degradation. In that moment, likely due to a voltage spike from adjacent high voltage bundles, a small spark jumped across a frayed wire. That tiny, invisible spark found the perfect fuel air mixture. The resulting explosion was instantaneous and catastrophic. The pressure wave ripped the aircraft apart, severing the nose and cockpit. Witnesses miles away saw a brilliant, rapid ascent, later proven to be the forward section of the burning fuselage still moving forward before it dropped, followed by a massive fireball. The aircraft had vanished. The crew had no time to radio any distress call. The entire sequence, from initial explosion to catastrophic structural failure, took mere seconds. The world was left with an impossible question. Was this an act of terror or something far more chilling? The explosive nature of the crash immediately led the FBI to seize jurisdiction, treating the crash site as a potential crime scene. This launched the most expensive and complex air disaster investigation in US history, costing over $40 million. The NTSB investigators, whose priority was safety, had to operate alongside the FBI's criminal probe, creating palpable tensions over evidence and control for months. The recovery effort was a military operation, with Navy vessels like the USS Grasp and USS Grapple using sonar and deep sea divers spending thousands of hours in hazardous conditions to bring up 95% of the aircraft from the seabed. The recovered pieces, totaling over 300 tons of debris, were transported to a massive hangar in Calverton, New York, where the NTSB's wreckage reconstruction group meticulously rebuilt the fuselage on an aluminum frame. This was the giant jigsaw puzzle. The reconstruction delivered the definitive evidence: petal shaped fracture patterns on the fuselage skin of the center section. These patterns are only created by internal pressure waves pushing outward, conclusively dismissing theories of an external missile or a typical cargo hold bomb. The point of origin was undeniable: the center wing fuel tank. The technical analysis focused on how an empty fuel tank could explode. The answer lay in the perfect storm of design and environment. The residual jet A fuel vaporized easily in the confined, heated space known as the ullage. The tank's design, which routed the hot air conditioner ducts directly underneath it, was the heat source. The NTSB determined that temperatures within the tank often reached 140 degrees Fahrenheit, 60 degrees Celsius, a lethal threshold for fuel vapor flammability on a warm day. The search for the spark was equally exhaustive. While no physical component was found, investigators traced the likely source to the fuel quantity indication system FQIS wiring. This low voltage system's wires, designed to be inherently safe, were found to be susceptible to voltage spikes when bundled alongside higher voltage aircraft wiring. The aging of the 25-year-old aircraft meant insulation, degradation, and potential chafing, creating a path for a momentary high energy arc to travel down the FQIS wires and into the explosive vapor. It was a failure of systems engineering, a low energy arc, an overheated tank, and a perfect vapor concentration. The NTSB's final report, approved on August 23, 2000, fundamentally changed global aviation safety. The investigation proved that fuel tanks are not inert under routine conditions. This led to the introduction of the Fuel Tank Safety (FTS) rule, enforced by FAA's Special Federal Aviation Regulation 88 SFAR 88. The installation of fuel tank inerting systems FTIS across the world's commercial fleet. This system uses an air separation module to bleed air from the engines, remove the oxygen, and fill the tank's ullage with non-combustible nitrogen-enriched air. This eliminated the threat of explosion. The tragedy of TWA Flight 800 became the safety catalyst the industry never knew it needed. The meticulous years-long investigation, born from the initial horror of an explosion, forced designers to eliminate a catastrophic flaw inherent in the 747's original structure. Though the 230 lives lost could never be recovered, their memory is enshrined in a profound and permanent layer of safety that protects every commercial flight today. The wreckage itself, after serving as a training tool for new investigators for 2 decades, was finally decommissioned and digitally archived, closing one of the most painful but ultimately most instructive chapters in aviation history.